Alright, in this video we'll be going through the 2018 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. The Electron rocket developed by New Zealand company Rocket Lab has begun commercial launches of satellites. The rocket can carry a satellite of 150 kgs to a stable circular orbit 5 times 10 to the 5 meters above the Earth's surface. Show that the force due to gravity on the satellite in this orbit is 1,270 newtons. Alright, so we know our Fg is equal to the gravitational constant times our big mass, little mass, all over r squared. Now remember, in this case, our r value is the distance between the center of mass of the two objects. So if we have our satellite up here, remember we can treat our satellite as a point mass as it's much smaller than the Earth, right? And we have our Earth over here, we have the Earth's center of mass. Our r value is the distance right here. So the distance between the two center of masses of the objects. Remember, this height right here is this height over here. So this is 5.00 times 10 to the 5 meters, okay? So we need to add the radius of the Earth right here, and that's 6.37 times 10 to the 6 meters, okay? So our r value is going to be 6.37 times 10 to the 6 plus 5.00 times 10 to the 5, and that gives an r value of 687,000 meters. Alright, so now we can simply plug in our numbers. We get our Fg is equal to the gravitational constant, which is 6.67 times 10 to the negative 11, times our big mass, which is the mass of the Earth, and we get 5.97 times 10 to the 24. Alright, let me just move this. And that's times our little mass, which has a mass of 150 kgs, all over 687,000 squared. And this gives an Fg of 1,265.54 newtons, and we can round that to 1,270 newtons. There we go, and you can see that's the value that we're trying to find. The rocket, the satellite, and any space debris at the same altitude in a stable circular orbit will travel at the same speed. Show that this is also true by deriving the formula for the orbital velocity, and use this to determine the orbital velocity of the satellite. So we know that when we are in orbit, our Fc is provided by Fg, right? And so therefore mv squared all over r is equal to g big mass little mass all over r squared. Right off the bat, we can cancel out our little masses, and we get v squared all over r is equal to gm all over r squared. And therefore we get v squared is equal to gm all over r, and therefore v is equal to square root gm all over r. And as you can see, this is the exact same equation up here, okay? And from here, you can tell that any object will travel at the same velocity at this altitude because the mass of the object that is in orbit, which is our little mass, is no longer in the equation. The only mass in this case is the mass of the Earth, and we obviously have the distance between the Earth and the satellite that's in orbit. Okay, so we can find that velocity, where we have our velocity is equal to square root the gravitational constant, which is 6.67 times 10 to the negative 11, times the mass of the Earth, 5.97 times 10 to the 24, all over our r, which we just found was this value right here, so 687,000, and we get a velocity of 7,613 meters per second. There we go. In the marking schedule, it also accepts this answer, 3.82 times 10 to the negative 8 meters per second. But even though the marking schedule accepts that answer is wrong, because you get that answer from using the little mass, so the mass of the satellite, rather than the mass of the Earth right here, okay? So even though the marking schedule accepts that answer is completely wrong. So if you got that answer, don't take it as a win that you got it. They're just giving it to you in this case to be nice. I think maybe a lot of people got that wrong when they took this exam, okay? So even though it's marked correct, it is actually wrong. A 20 kg piece of space debris is traveling at the same altitude and speed as the satellite, but in a direction that is 90 degrees to the satellite's velocity. At a moment shown in the diagram below, the debris and satellite are 1.08 times 10 to the 4 meters apart. Calculate the distance between the center of mass of the system and the satellite. So we know our equation for center of mass is x center of mass is equal to m1x1 plus m2x2 all over m1 plus m2. Now in this question, we want to calculate the distance from the satellite, so we can set our satellite as our reference point. So we can set this as x1, and therefore x1 is equal to 0 meters because that is our reference point, okay? And that means right off the bat, we can just cancel out this term, and we get x center of mass is equal to m2 x2 all over m1 plus m2. And so therefore, as we set the satellite to x1, that means the satellite is also m1, which is 150 kgs, right? We got that from the previous question. And so that means this right here is x2, and that is 1.08 times 10 to the 4 meters, okay? That is the distance right here. And the satellite is given as 20 kgs, and so m2 is equal to 20 kgs. Now we can simply just plug in our numbers, and we get 20 times 1.08 times 10 to the 4, all over 20 plus 150, and we get a center of mass of 1,270 meters. There we go. Describe the motion of the center of mass of the system as the debris and the satellite continue to move along their paths. Justify your response. Okay, so because there are no external forces, that means momentum is obviously conserved. The center of mass of the system will continue to move at the same velocity. And so because we know velocity is a vector, it has both direction and magnitude. If I say it continues on with the same velocity, I mean it will continue with the same magnitude, meaning it will continue with the same speed, and also the same direction. So the direction and speed of the center of mass will not change. All right, you can write that down. The debris collides and becomes embedded in the satellite. Calculate the speed and direction relative to the initial direction of the satellite and embedded debris. So this is a question about momentum, and in order to solve this, we obviously need to use our vector triangles. Okay, you can see right over here, this is what the situation looked like before. Okay, so this is the before state, and we can see that the momentum of the debris was in the direction to the right. All right, so we can make that over here as our first vector. Okay, and the momentum of the debris is obviously equal to the mass times its velocity. We know its mass is 20 kgs, and we know its velocity because every single object at that same altitude was moving with this velocity right here. So that's 7,613. And that gives a momentum of 152260 kg meters per second. There we go. And similar thing for the satellite, we can see that its momentum is upwards, right? So we can draw that vector right here, like so. And we can figure out the momentum of the satellite. Again, mass times velocity. We know the mass of the satellite is 150 kgs times the velocity, again, which is the same as the debris. And this gives a momentum of 114195 kg meters per second. There we go. Okay. And therefore, we can calculate the final momentum as this resultant vector right here. Okay. We also know that this is a right angle. And so therefore, using Pythagoras, we can find the momentum of our resultant vector, which will be our final momentum. And so therefore, our final momentum is equal to square root 152260 squared plus 114195 squared, and this gives a final momentum of 1152055.949 kg meters per second. All right, and because we want to calculate the speed, we know our final momentum is going to be equal to the mass of the entire system times the new velocity. Okay, we can rearrange for velocity, and we get the velocity is equal to the final momentum all over the mass of the system, and therefore plugging in our numbers, we get 1152055.949 all over the mass of the entire system, which is 20 plus 150. And this gives a final velocity of 6,777 meters per second. There we go. Now, it also asks us to find the direction, so we need to find an angle. The angle that we need to find is this angle right here, because we are trying to find the angle that is relative to the initial direction of the satellite. The initial direction of the satellite was straight up and down, and so therefore we can find the angle relative to the satellite as the satellite is now moving in this direction right here. So therefore, we get our theta is equal to the inverse tan of the momentum of the debris, which is this value right here, and this is the momentum of the satellite, all over the momentum of the satellite, and therefore inverse tan of 152260 all over 114195, and this gives an angle of 7.59 degrees. There we go. Weather satellites can be launched into orbits that circle around the North and South poles. This enables the satellite's camera to view the whole of Earth's surface as the Earth spins underneath. The orbital period of a typical weather satellite is 101 minutes. Show that in order to keep the camera pointed towards the Earth's surface, the satellite must spin at an angular velocity of 1.04 times 10 to the negative 3 radians per second. So we know our angular velocity is equal to 2 pi all over t. We are given our t, but our t value is in minutes, and we obviously know that we need that in seconds. So we have 101 times 60 to get it down into seconds, and this gives us 6,060 seconds. And so therefore we can just plug that in, 2 pi all over 6,060, and this gives an angular velocity of 1.0368 times 10 to the negative 3 radians per second. And obviously we can round that to 1.04 times 10 to the negative 3 radians per second. There we go. This angular velocity is achieved by firing 2 5-Newton thrusters attached to opposite sides of the satellite's 1.6 meter diameter. Explain why 2 thrusters must be used rather than simply 1 thruster on one side of the satellite with double the thrust force. Okay, so if we have our satellite over here, okay, like so, and we have a thruster over here and a thruster over here, okay? And so this one is thrusting over here with 5 newtons, and this one is thrusting this way with 5 newtons, okay? So I want you to keep this sentence in mind when I go through this. In order for rotational acceleration to be pure, the torques must be additive, meaning they must add together, but the forces must cancel out, okay? And so what that means is, we can see here, if we just look at the torque, for example, we can see here, we are applying a force at a distance to the axis of rotation right here, and this distance is given as 0.8 meters, okay? We can see that this force is gonna make the satellite rotate in this direction right here, okay? Now let's look at this thruster. We can again see the force applied at a distance of 0.8 meters, okay? And so therefore, this thruster is going to make the satellite move in this direction. And as you can see, the 2 satellites are working together to rotate the satellite in a clockwise direction, okay? Now, don't write clockwise in your answer. I'm just doing this as a depiction. It could be anti-clockwise. It could be in any direction, to be honest. For my depiction, it's in the clockwise direction, all right? However, if we just purely analyze the forces, we can see that our horizontal forces are equal to 0, okay? There are no thrusters in the horizontal directions, but our vertical forces, we can see if we take upwards as positive, okay, we can see we have positive 5 newtons minus 5 newtons coming down. And therefore, the sum of all forces in the vertical direction is equal to 0 newtons also. And so, like I said at the start, in order for rotational acceleration to be pure, the torques must be additive, meaning that these thrusters produce a torque in the same direction, which they do. They produce it in the clockwise direction in my example. But the forces must cancel out. And as you can see, they cancel out because they go in opposite directions. However, if we just have a satellite like this, okay, and we just have one thruster right here, and this thruster is producing 10 newtons of force. I'm sure you've seen this somewhere in maybe like in movies or something, but if we only have one thruster here, we can imagine that this satellite is just going to spiral in this direction like this. So if we only have one thruster, what that would result in is an unbalanced force, okay, unbalanced force. And therefore what this will result in is a change in motion of the center of mass, all right? And you can write that in. The thrusters are fired for 6.48 times 10 to the negative 3 seconds to set the satellite rotating at a required angular velocity. Show that the rotational inertia of the satellite is 50 kg meters squared. So there are 2 ways to solve this problem. The first one being, we can use our kinematic omega finally is equal to our omega initially plus alpha t. We know our omega initially was equal to 0 radians per second, okay? It wasn't rotating at all. However, our omega finally is given up here as 1.04 times 10 to the negative 3 radians per second. So we get 1.04 times 10 to the negative 3 radians per second. And therefore, we can rearrange for our angular acceleration, and we get omega finally minus omega initially all over our time is equal to our angular acceleration. Therefore, 1.04 times 10 to the negative 3 minus 0 all over our time, which is given up here, 6.48 times 10 to the negative 3. And this gives an angular acceleration of 0.1605 radians per second per second. Now we know our torque is equal to I alpha, and therefore our I is equal to our torque divided by our alpha. We just found our alpha value, however we don't know our torque. What we do know is that torque is also equal to force times distance, okay? And we know from the previous question that we have 2 forces being produced at a distance of 0.8 meters. And so therefore we have 2 thrusters producing a force of 5 newtons at a distance of 0.8 meters, and this gives a torque of 8 newton meters. There we go. And so simply we can plug this value into here and this value into here, and we get our rotational inertia is equal to 8 all over 0.1605, and this gives a rotational inertia of 50 kg meters squared. There we go. And as you can see, that is the answer that we're looking for. The second way in which we can solve this, we know that our change in momentum is equal to our force times our time. Okay, we know we have two thrusters producing a force of 5 newtons over a time period of 6.48 times 10 to the negative 3 seconds. Okay, and this gives a change in momentum of 0.0648 kg meters per second. And so therefore, because we know our change in momentum, we can figure out our change in angular momentum. So our change in angular momentum is equal to the change in momentum times our radius. Okay, where this equation comes from, we know our angular momentum is equal to mvr, right? But we also know that our momentum is equal to mv. And so we can simply plug this into here and we get our angular velocity is equal to our momentum times our radius. Okay, so therefore, calculating our change in angular momentum, we get 0.0648 times our radius of 0.8 meters. And we get our change in angular momentum as 0.05184 kg meters squared per second. Okay, we know that our angular momentum is equal to I omega, and so therefore our I is equal to our angular momentum all over our omega. We found our omega in the first question all the way up here, this value right here, and so therefore 0.05184 all over 1.04 times 10 to the negative 3 is equal to 50 kg meters squared. There we go. Instead of using two thrusters to adjust the angular velocity of the satellite, it is often preferable to use a reaction wheel system. When the wheel begins to turn in one direction, the satellite will turn in the opposite direction. The wheel is solid and has a rotational inertia of half mr squared. The radius of the wheel is 0.2 meters and the mass of the wheel is 5 kgs. Calculate the angular velocity of the wheel required to keep the camera pointed at the Earth. State any assumptions. So the assumption in this calculation is that there are no external forces and therefore there are no external torques, meaning that angular momentum is conserved. So we know our I is equal to half mr squared, right? So now plugging in our numbers, we get half times the mass of the wheel, which is 5 kgs, times its radius, which is 0.2, and that's all squared. And this gives a rotational inertia of 0.1 kg meters squared. There we go. So now remember that is the rotational inertia of the wheel. Now in the previous question, we calculated the angular momentum of the satellite. That's given right here, okay? So angular momentum of the satellite is equal to 0.0518 kg meters squared, okay? And if you wanted to calculate that value again, we know that our angular momentum is equal to I omega, and we found in the previous question that our rotational inertia was 50 kg meters squared, and so that's 50 kg meters squared times 1.04 times 10 to the negative 3, and that gives our answer right here, okay? Now, because angular momentum is conserved, we know that the angular momentum of the satellite is equal to the angular momentum of the wheel, okay? And so therefore, the angular momentum of the wheel is equal to I omega, all right? And remember, we're trying to find our angular velocity value, and so therefore we can rearrange for the angular velocity and we get the angular momentum of the wheel all over the rotational inertia of the wheel, and therefore we can plug in our numbers and we get 0.0518 all over 0.1, and we get an answer of 0.518 radians per second. There we go. When astronauts return to Earth, a spring under their seats reduces the force during their landing. The astronaut's kinetic energy is converted to spring's potential energy as the spring is compressed. If there is no friction, this will set the astronaut into simple harmonic motion. State the conditions required for the astronaut's motion to be considered simple harmonic motion. Alright, so this is our classic question. The restoring force must be proportional and in opposite direction to the displacement. And you can write that in. During landing, an astronaut and seat had a combined mass of 80 kgs and were set into simple harmonic motion with an amplitude of 0.15 meters and a period of 0.94 seconds. Determine the spring constant of the spring. Alright, so we know our T is equal to 2 pi square root m all over k. And therefore, simply just rearranging for k, we get T all over 2 pi is equal to square root m over k. We can square both sides to get rid of that square root, and we get m over k. And therefore, k is equal to m divided by t divided by 2 pi squared. And therefore, plugging in our numbers, we get 80 all over our period, which is given as 0.94 all over 2 pi, and that's all squared, and this gives a spring constant of 3,574 Newton per meter. There we go. So this is part 2 of the previous question. It also wants us to calculate the amount of energy stored at the spring at maximum displacement. Alright, so we know our EP is equal to half kx squared, again where our x is our displacement. And so therefore we can simply plug in our numbers. We just found our spring constant, and that was 3,574 times our displacement, which is given up here with a amplitude of 0.15 squared, and this gives an EP of 40.21 joules. There we go. Using a reference circle or otherwise, determine the velocity of the astronaut when the astronaut is 0.1 meters above the equilibrium position. Alright, so we're starting at the equilibrium position, and we want to find our velocity once we get 0.1 meters above the equilibrium position, okay? And so we can draw our phasor over here, like so. This is a right angle triangle. Again, this distance is 0.1 meters, and this distance is 0.15 meters, okay? That's our amplitude, right? That's our radius. And so therefore, we need to find this angle right here. Drawing that right angle triangle out bigger, theta 0.15, 0.1. We know that theta is equal to the inverse sine of 0.1 all over 0.15, and this gives a theta value of 0.7297 radians. Alright, and so therefore, as we're starting at the equilibrium position, our velocity is equal to a omega cos omega t. Now remember, theta is equal to omega t, and so we can simply plug this into here, and we get cos theta instead, okay? And so therefore, we get our velocity is equal to our amplitude, which is 0.15, all over omega, which is 2 pi, all over our period of 0.94. So plug in 0.94 times cos theta, which is 0.7297, and this gives a velocity of 0.747 meters per second. There we go. The motion of the astronaut is quickly brought to rest by a damping system on the spring. Damped harmonic motion can be modeled in a laboratory with a mass, spring, and beaker of water as shown. Discuss how damping will affect the amplitude and period of the harmonic motion of the mass on the spring. In your discussion, you should include a description of what is meant by damping, a description of the damping force in the laboratory model and how it will impact the motion, a sketch of a graph of the position of the mass versus time starting at the moment the mass is released from the maximum downward displacement. So damping is a regular reduction in displacement of a simple harmonic motion system. This reduction in displacement is due to an external force which acts opposite to the restoring force, thus removing energy from the system. So in this case, when the mass is pushed down and then released, and therefore the mass will move up again, right? So when the mass is moving up again, the damping liquid will provide a frictional force which will act in opposite direction to the motion. And so if the motion is upwards, this frictional force will act downwards, okay? So again, like I said, it's in opposite direction to the restoring force, right? Because our restoring force is the spring, which is trying to bring the mass upwards, and so this friction force is acting downwards, okay? Once the mass reaches the top, it's going to want to move back downwards again, okay? And when that occurs, the damping liquid will provide a frictional force, but in the opposite direction this time, it will provide it upwards, okay? And again, that is in opposite direction to the restoring force, because the spring in this case is trying to move the mass back down, okay? Now, remember, as the period is equal to 2 pi square root mass all over our spring constant, the period in this case will not change, and therefore, as our frequency is equal to 1 over t, if our period does not change, our frequency also will not change, okay? And so, therefore, this damping force, or this frictional force caused by the damping liquid, will remove energy from the system, and therefore the amplitude will slowly decrease over time. And so this will look like something like this, okay? We have our first period, our second period, and our third period, okay? And we would have positive 0.150, and this will be negative 0.150, and it will look something like this. Hold on. Like this. And as you can see, there is a regular reduction in amplitude causing this shape right here, okay? And with that, we are done. See you.